You are listening to The Vocal Technologist. Spoken tech for your ears.
If you're running any big data operation today, it feels like you're always just one bad config file away from, well, disaster. It's almost a low-grade terror.
Yeah, absolutely. The pressure to keep things running and running fast while the whole landscape shifts under your feet, it's intense.
And the scale is just mind-boggling now. We're not just talking about moving data anymore.
No, the game's changed. It's all about how you minimize the complexity, the moving parts, and maximize reliability. Especially when you hit these massive scales, failure isn't really an option.
Exactly. And that's what we're digging into today. We've got a whole collection of technical insights, real-world examples of how companies are tackling this on the front lines.
Right, looking at everything from streaming data to query engines, AI, RAG, databases, the works.
The goal here is to pull out the really surprising innovations, the practical stuff you can actually use if you're building these kinds of systems.
And the common thread really is that relentless push for predictability and performance, but doing it simply, or, well, as simply as possible at this scale.
Okay, let's start with moving the data itself. This seems like a high-wire act sometimes. Think about Pinterest. They're moving hundreds of terabytes daily from sharded MySQL. That's change data capture CDC on a level most people don't even think about.
It's huge. And yeah, they lean heavily on Kafka Connect, with Debezium doing the actual capturing from the database logs. That's fairly standard, I suppose.
But there's got to be a trick to doing it reliably at that volume.
There is. The clever part is how they architected it. They decoupled the configuration management from the streaming logic itself. Big separation.
Ah, okay. So if you need to tweak a setting for one data source or reroute something.
You don't bring the whole pipeline crashing down. You can update configs, maybe restart a specific connector instance without halting the entire flow. It buys you resilience during maintenance or changes.
Makes sense. But what about the classic streaming nightmare? Exactly once semantics. How do they guarantee data isn't lost or, maybe worse, duplicated if something hiccups during that massive transfer?
Right, that's the ghost in the machine, isn't it? Duplication on recovery. Their solution is pretty neat. It involves metadata synchronization.
Okay. How does that work in practice?
They essentially embed transaction IDs and offsets from the source database directly into the Kafka records metadata. So during a recovery, if a message gets replayed because of a failure,
The system can check that source transaction ID.
exactly. It checks if that specific transaction ID has already been processed and committed downstream. If yes, it just drops the duplicate. It makes the replay idempotent, safe to run multiple times. The source holds the truth.
Elegant. Okay, so that's ingestion. Let's shift to querying. Uber's challenge hundreds of millions of queries daily, low latency needed for analytics, tracing.
Yeah, a massive analytical workload. And they initially built this complex layered system called Neutrino based on Presto.
Which, layers often mean complexity, right?
And that complexity bites you eventually, operational headaches, maintenance burden. It just became too much, especially for their OLAP use cases, those complex analytical queries over historical data.
So they didn't just throw more servers at it. They simplified, moved to Apache Pinot. What was the core architectural change there that gave them the win?
The big shift was adopting Pinot's newer multi-stage engine, specifically in what they call light mode. Think of it as going brokerless.
Brokerless. How does that simplify things?
Well, traditional engines often have a central coordinator, a broker, that manages and routes parts of the query. The multi-stage engine distributes that logic. The workers, the nodes holding the data, can execute query stages directly, talk to each other.
Less bottleneck at a central point.
Exactly. It reduces latency, gets rid of that complex central coordination layer, and makes the whole thing more robust. It's a great example of gaining performance and reliability by actually removing architectural complexity.
All right, switching gears a bit. AI and data. For a while, our big retrieval-augmented generation was the hot topic. Feed relevant documents to an LLM.
It was everywhere.
But things move fast. Is it already old news?
I wouldn't say dead, but it's definitely evolving. Maturing, maybe. We're seeing it become part of a much more rigorous discipline, something people are starting to call context engineering.
Context engineering. I like that. Sounds more deliberate than just retrieval. So what does that involve beyond just finding some documents?
It's about being much more precise and structured with the information you feed the AI. Think advanced query rewriting, refining the user's question before you even search, or really careful selection of custom encoders tailored to your data.
Okay.
And critically, strong guardrails. input validation, output checks. Plus, moving beyond just dumping stuff in vector stores. Serious enterprise ag or context engineering is integrating knowledge graphs.
Knowledge graphs, why are they so important here?
Structure and explainability. When an AI agent gives you an answer based on retrieved data, you need to know why. Which specific facts led to this conclusion? Knowledge graphs provide that structured pathway, that provenance.
Right, so it's not just a black box spitting out answers. You can trace the reasoning.
Precisely. And that trustworthiness becomes absolutely vital as these systems become more autonomous, more like agents that take actions.
Which brings up another interesting point from the material. These AI agents, they fail in different ways depending on their job. A coding agent breaks differently than a data analysis agent.
That's a really key insight. Code is, relatively speaking, structured. You can often test if it works deterministically. Data, especially raw business data, is messy. An LLM trying to summarize vast amounts of it can easily lose critical nuance or context. It hallucinates differently.
So if you just fire hose raw data at an analytics agent, it can get overwhelmed and basically make stuff up.
Pretty much. It struggles to reason reliably when the context window is overloaded with just raw tables or logs.
So what's the fix? How are folks like Hex dealing with this data overload problem for their agents?
The key seems to be making limitations explicit. They build what they call structured context maps, sort of pre-digested views of the data. They enforce strict token limits, and crucially, they make data truncation explicit.
Meaning the agent is actually told what it didn't see.
Yes. Warning. I could only analyze the first 10,000 rows of this million-row data set. That way the agent, and the human overseeing it, understands the boundaries of its analysis rather than confidently asserting something based on incomplete info.
That seems essential as we head into this agentic era. So if you're building data infrastructure to support these agents safely, what are the must-haves?
The thinking coalesces around 3 pillars. First, semantics. You need a curated metrics layer. Agents shouldn't hit raw tables. They should query well-defined business concepts.
Like customer churn rate, not select count from table X where.
Exactly. Second, speed. Analytics needs to be near instant, sub-second ideally. Why? So the human user can quickly sanity check the AI's work without losing their train of thought. It keeps the human truly in the loop.
Right. And the third?
Stewardship.
Okay.
This covers all the governance aspects, robust guardrails, clear human oversight procedures, versioning of data and metrics. It's about ensuring the AI remains a helpful assistant, not an uncontrolled actor.
Okay, let's dive even deeper, under the application layer. Big shifts are happening in core infrastructure. Kafka, for instance. For years, the model was brokers with local disks.
Right, stateful brokers.
But cloud-native thinking is pushing towards Kafka going diskless. An irreversible shift, as the material puts it.
It's a major trend. The traditional Kafka setup, with brokers storing data locally and replicating it across availability zones, it gets expensive. Storage costs, replication traffic, managing those stateful brokers.
So the idea is to separate the compute from the storage.
Exactly. Let the brokers be primarily compute nodes, handling connections, processing messages, and push the actual durable storage off to cheaper, more scalable object storage like S3. It shrinks the broker footprint, cuts replication overhead.
And there are a few different approaches emerging. Slack, Aven, AutoMQ.
Yeah, they're all tackling it slightly differently, but converging on that core idea. Slack's fast tiering aims to offload older log segments to object stores quickly. Aven's proposing diskless topics, where the broker is truly stateless. Object storage is the source of truth. AutoMQ is working on a unified shared storage model to bridge both worlds.
But the direction is clear.
Yeah.
Decouple broker compute from durable storage for cloud efficiency.
Definitely. Makes a lot of sense at scale.
And speaking of storage efficiency, let's talk file formats. Iceberg v3 seems like a pretty big deal, particularly around how updates are handled.
It's huge. The introduction of deletion vectors changes the game for updates and deletes in large data lakes.
How so? What was the pain point before?
Think about needing to delete or update just one row in a massive Parquet or ORC file, maybe a gigabyte or more. Traditionally, you had to rewrite the entire file. That's incredibly expensive. Tons of I/O, tons of compute, called copy on write.
Right. Makes CDC or minor corrections painfully slow and costly. So deletion vectors avoid that.
Precisely. Instead of rewriting the huge data file, Iceberg v3 lets you write a tiny companion file, the deletion vector, that basically just lists which rows in the original file should be ignored.
Like a little mask file.
Kind of, yeah.
Yeah.
It enables efficient, row-level updates and deletes without those massive rewrites. The benchmarks show significant speedups, like up to 4x faster merge operations. And it means file compaction shifts from being this constant, necessary evil to more of an occasional background optimization.
Very cool. Okay, one more fundamental shift down at the process level. The idea of thread per core being dead. Why is that old parallel processing model fading?
It's just too rigid for modern, bursty, unpredictable data workloads. If you dedicate one thread to one core for one task, and that task finishes early, or maybe it was small to begin with.
The core sits idle while others might be totally swamped.
Exactly.
Yeah.
Wasted resources. The move is towards async runtimes, like you see in Rust and other modern systems. They use dynamic work stealing approaches.
Work stealing.
Yeah, imagine a shared queue of tasks. When a thread on a core finishes its current job, it can go and steal the next available task from that shared queue rather than sitting idle. It leads to much better load balancing, especially when tasks have wildly different sizes or durations, which is common in data processing.
So shared state concurrency helps handle that unpredictability better.
Much better. It's fundamental to building these high-performance, resilient platforms today.
Let's make this concrete. How does this apply in, say, a super time-sensitive scenario? Netflix. Recommendations during a live event, like an NFL game, millions of people watching. How do they push relevant updates to everyone instantly without melting their servers?
It's a clever two-phase approach to manage the load. Phase one is prefetching. While you're just browsing Netflix normally, maybe hours before the game, they're already sending potential recommendations down to your device via GraphQL. They distribute the heavy lifting over time.
So the recommendations are sort of preloaded, waiting.
Exactly. Then, phase two, at the critical moment, the big touchdown, whatever, they don't send the full recommendation data again. They broadcast tiny, low cardinality messages over WebSockets to potentially 100 million plus devices simultaneously.
Low cardinality meaning very simple messages.
Extremely simple. Maybe just a state key, a timestamp, perhaps an ID pointing to which prefetch recommendation to display now. It's a lightweight trigger. Your device gets this tiny message and immediately surfaces the relevant content it already has. Minimal data transfer at the peak moment.
That's smart. Distribute the heavy work, use a tiny trigger for synchronicity. Okay, one last area back to basics almost. Databases, Postgres, KV stores. We talk about Iceberg making updates cheaper, but why are writes inherently more complex or expensive in traditional systems?
It really comes down to correctly classifying your workload. Is it read-heavy or write-heavy? Most typical relational databases, like Postgres, are overwhelmingly read-heavy, maybe 10 reads for every write, or even more. And writes are fundamentally more complex. You usually have to update not just the data table, but also multiple indexes. Plus, you have the write-ahead log, the boolean, ensuring atomicity and durability. All that adds overhead.
And if you get that classification wrong, like you over-index a database, it's mostly reads.
You kill your write performance. Every single write now has to update all those extra indexes unnecessarily. It's a classic tuning mistake.
And then on the other side, you have systems optimized for writes, like many key value stores.
Right. If you peek under the hood of systems like LevelDB or RocksSDB, they often use append-only files and compaction techniques. They build log-structured merge trees or LSM trees. The architecture is deliberately designed to make writes super fast, just append to a log at the cost of making reads potentially a bit slower, as you might need to check multiple files. It's always a trade-off, based on the expected workload. Hashtag tag tag that total.
Wow, okay, we've covered a ton of ground. From Pinterest decoupling config and streaming for resilience, to Uber simplifying their query engine with Pinot's brokerless design.
And seeing RRA evolve into this much more rigorous context engineering discipline, realizing that AI trustworthiness really depends on structuring and limiting the data it sees.
Yeah, the theme seems to be smarter architecture, better structure, leads to more reliable and performant systems. Here on The Vocal Technologist, we usually focus right on the tech, but connecting these dots, it really highlights a critical non-technical factor, doesn't it?
Absolutely. Effective human supervision. All the context maps, guardrails, and semantic layers are crucial, but the material implicitly warns against weak human oversight.
Meaning, if the human is just clicking approve on whatever the AI suggests without real scrutiny.
Then all the tech doesn't prevent potential errors or biases from getting embedded or scaled up. We saw failures like the Dutch Sierra system referenced a reminder that nominal oversight, just rubber stamping, can be insufficient, even dangerous.
So it's not just about building a smarter agent with better data handling. The real challenge, maybe the next frontier, is designing the process around it so the human remains truly informed and in control, not just compliance theater.
Couldn't agree more. Applying these technical innovations requires that parallel effort in rigorous, context-aware human processes, technical excellence plus vigilant stewardship.
So think about your own stack. Where
Yeah.
can you decouple? Where can you simplify? Are your agents operating with clear, explicit boundaries? Food for thought. Apply these ideas, keep building, and we'll catch you next time.
Spoken Tech for your ears.